Hi, my name is Olga, and I will be presenting methods for matrix language determination in code-switched text and speech. Without further ado, let's get to the first part, the introduction. In the introduction, I will start with a few remarks on the background of code switching and the hypotheses. So first of all, what is code switching? Code switching is a process of speaker changing between languages within a single language production act, meaning within a conversation or text. This means that the speaker of the is a multilingual, which is fluent in several languages that they code switch in. The example on the slide demonstrates English Mandarin code switching in colloquial Singaporean language. Even only knowing the English language, you can observe that the English words used in this code switched utterance are mostly content words, while function words come from Mandarin. This way, you can say Mandarin grammar is providing the structure for the utterance. So this is something that matrix language frame theory tries to explain. The linguistic matrix language frame theory is introduced by Carol Muir-Scotton in 1993 in a book called Dueling Languages. The theory provides a model for code switch production and introduces the concept of main, dominant language, and a secondary inserted language in code switched utterances. These languages are called matrix language and embedded language. Alongside the matrix language and the embedded language, the matrix language frame theory introduces two methods for matrix language determination. So it's the morpheme order principle in matrix language and embedded language constituents consisting of singly occurring embedded language lexemes and any number of matrix language morphemes. Surfem's morpheme order will be that of the matrix language, and the system morpheme principle, which says that all system morphemes will come from the matrix language. The reason why I have underlined some parts of these principles is because the principles present certain features of the matrix language, and actually the morpheme order principle conceals two features of the matrix language: that the matrix language is the language of the context if the embedded language insertions are singly occurring, and secondly, that the matrix language is the language that provides the morpheme order. On the other side, if we look at the solutions for automatic text and speech processing for code switching, we will see that only some ideas from the matrix language frame theory have been used to automatically analyze speech or text. Usually, the idea of semantic and grammatical well-formedness is used as an argument for creating simulated code switch text from monolingual. While these ideas are useful for code switched text generation and simulation, almost none of them have touched upon the idea of the matrix language identity. However, the principles for matrix language determination are quite specific. An automatic matrix language identity classification for code switched text was only carried out in a single work and was never performed automatically for code switched speech. Alternatively, one can distinguish between languages in code switched text and speech using LID, language identity, which may be defined at different levels of data, frame-wise, token-wise, or utterance-wise. This was shown to be useful in text and speech processing applications, but using LID in applications does not inform the systems of the grammatical structure or the main language used in a code-switched utterance. Therefore, the following hypotheses had to be proven: that P1.1, P1.2, and P2, which would be derivatives of the principles, of the two principles mentioned before, are a better determiner of main language spoken in a code switched utterance than conventional language identity language segmentation approaches, and that the above principles are different to language identity language segmentation because they detect the main language based on the grammatical structure of the utterance rather than pronunciation. With this, let us move on to the method definition of these principles. A few slides back, we were looking into two linguistic principles for matrix language determination: morpheme order principle and system morpheme principle. In this work, the principles were reworked into three implementations: principles P1.1, P1.2, and P2. As the name suggests, the morpheme order principle was split into two principal implementations, now paper: the single tone principle P1.1 and the token order principle P1.2. The P1.1 singleton principle represents the first part of the morpheme order principle from the MLF theory and says that the matrix language is the language that provides context for singleton insertions from another language. P1.2 describes the second part of the morpheme order principle, which tells us that the matrix language is the language that provides the morpheme order from the utterance. And finally, P2 is based on the system morpheme principle, and it says that there are specific parts of speech that may only occur from the matrix language and not from the embedded language. These often coincide with function words, which contribute to the grammatical structure of the utterance. Now that the implementations of the principle for matrix language determination have been defined, let us talk about the implementations of the principles described in previous slides. For the aforementioned monolingual language models, transformer architecture and Colholm datasets are used. These monolingual language models are used for the implementation of the principle P1.2. Apart from that, scaling factor estimation of the monolingual language models for P1.2 is performed using monolingual utterances from CME and Miami. The testing is carried out on code-switched utterances from the two corpora. Apart from the data, a pre-trained post-tagger is used for P2 implementation. A baseline pre-trained ekappa TDNN is used for utterance LID prediction, and a simple multilayer perceptron is used to train mappings from pre-trained LID outputs to custom LIDs and also acoustic MLIDs, so matrix language identities. Finally, you can look at the outcomes of the experiments. The examples on the slides, the examples of applying the principle to text is on the slides. As you can see, it is similar to utterance LID. You may also observe that there may be discrepancies between the principles. The baseline implementation is the token LID majority. The matrix language, which says that the matrix language is the language that contributed the most tokens to a sentence. Upon applying the matrix language identity determiners to code-switch datasets, we can compare the distributions of LIDs and MLIDs. In this table, token LIDs for code-switch sentences and utterances are defined, and utterance LIDs for monolingual sentences are shown in the first two rows. The matrix language identities are presented at the three bottom rows. In the table, we can observe that the distribution of LID shows the dominance of the English tokens and utterances in most cases. However, if we look at the distributions of matrix languages, one can see that grammar used by multilinguals is predominantly non-English, meaning Mandarin and Spanish. Having the automatic annotations from P1.1, P1.2, and P2, one can use these training labels for LID system adaptation. In the table on the slide, columns P1.1, P1.2, and P2, and rows MCC, P1.1, P1.2, and P2 represent textual matrix language identities without unknown values. So here, further, LID column is pre-trained LID system without adaptation. LID map is a pre-trained LID system outputs mapped to monolingual LID labels from the target corpora, in this case Miami. MLID P1.1, P1.2, and P2 are also trained mappings, but instead of monolingual LID labels from Miami, code-switched MLID are used from the three textual MLID determiners. First thing that we notice is the coverage of P1.1 and P2 is far from 100% at 60 and 58%, while P1.2 is at full 100% coverage. Since P1.1 and P2 are rule-based, we regard the outputs of these principles as almost gold standard, the correlation between the principles also being very high, which is 0.81. For the Miami corpora, P1.2 has a high agreement with P1.1, which is 0.38, and relatively low agreement with P2 of 0.09. This may indicate that P1.2 for English-Spanish code switching is not the best determiner of MLID, because P1.2 determines the MLID based on the word order, and word orders for English and Spanish are relatively similar. Miami has a small subset of annotated utterances. Therefore, it is possible to calculate F1 score, which is 100 for P1.1, 67 for P1.2, and 93 for P2 for the textual MLID determination task. For the acoustic MLID determination task, the highest F1 macro is for the P1.2, while the highest correlation is for the P2 principle. There is no annotated matrix language identity data for CME, but correlation value for the principles can be analyzed instead. 0.83 for P1.1 and P2, while correlations with P1.2 are generally lower, 0.36 and 0.31. If the textual principles are used as ground truth labels for acoustic MLID training, then acoustic P1.1 turns out to be the best predictor for all the principles, including itself. So finally, the contributions of this work are the following. Principles P1.1, P1.2, and P2 for MLID from text were implemented closely following the MLF theory. Applying the principles to code switch datasets has shown that non-English languages, Mandarin and Spanish, are preferred over the English language as the matrix language, contrary to the monolingual choice of textual LID. And matrix language identity predictors from speech were trained using P1.1, P1.2, and P2 and compared to acoustic utterance LID. Overall, this research will help advance analysis of code switch text and speech and improve performance on downstream tasks for code switching. Thank you for your attention, and please reach out to me via email if you have any questions.